Now, time for a conversation about cycloalkanes. Cycloalkanes are very similar to their non-cyclic relatives, where you have single bonds between carbons and hydrogens, same between carbons, but now the carbons are in a ring, so the carbons don't have any end carbons. They're always all connected around in some kind of a cyclic structure. Here are cyclopropane and cyclobutane. As you will notice from the things we've talked about before, the more carbons you have, the higher the boiling or melting points. Same thing applies with cyclic compounds, just the same idea, just different values. We don't have to memorize their values. And the boiling points are always higher than the melting points. These compounds are kind of strained because they have very tight geometry, and that makes them kind of crazy and reactive, because you kind of have to have about 60-degree angles to make a triangle in cyclopropane and about 90 degrees angles in cyclobutane. Those are not normal geometries for carbon compounds. They're usually never less than 109 most of the time, the ordinary tetrahedral geometry. So they're kind of peculiar for their strained geometries. So when we're talking about cycloalkanes, this is in comparison to where we previously discussed acyclic alkanes. In other words, A means not. They have no rings. Oops, sorry. I touched the wrong thing. The acyclic compounds we began with have no ring structures, and they're otherwise known as open chain compounds. So cycloalkanes are going to have some type of ring of carbons. Their properties are very much like the other alkanes in terms of flammabilities, boiling point patterns, solubility in water and lack thereof, and odors and density compared to water. So their properties are very similar to the things previously described for every other alkane. The main difference, though, is that they are more rigid. They have no loose ends. They do have some twisting and bending properties to a certain extent, but they're much more rigid than acyclic compounds. It turns out that cyclohexane, C6H12, as in shown here, and I'm sorry that these pictures are a little bit truncated. I wasn't sure they didn't realize that. Cyclohexane has specific shapes that it tends to be able to form, and they have names because they're specific shapes that we call conformations, and one of them is a chair conformation, and it turns out to be relatively stable. If you draw these in a three-dimensional fashion, and this is going to be hard for you to tolerate, you're not going to like this, but if you looked at your cyclohexane ring just right, you could put it like this, and if you use your imagination hard enough, that could look like a chair, kind of. And so the cyclohexane is characterized by having that type of geometry that we call a chair structure. The chair structure of cyclohexane is important because it's very much the nature of the structure of glucose that will be very important as we discuss carbohydrates much later in the course. All right, so here's cyclopentane, where all the bond angles are relatively close to 109, and cyclohexane, where they are pretty close to exactly the ordinary tetrahedral geometry. Notice that every corner still has 2 hydrogens because carbon has 4 bonds. All right, so what are we going to do else with cycloalkanes? We're going to talk a little bit more about them in terms of how we draw them and name them, because we have already used them a little bit without a lot of detail, but I've told you that corners are carbons. And we draw these line structures, and we don't draw the carbons. So it's a shorthand method to represent these rings using polygons, yay for geometry. And we don't draw the carbons. And you're welcome to do so if it helps you, but you won't see them that way in the representations often. So how do we name these things? We're going to use the cycloalkane name as the parent or last name, and we'll see that at the end of the name. And then the substituents are going to be attached to the corners of the cycloalkane ring. And the trick is that you have to start with the substituent that has alphabetic priority. So pay attention to alphabetic order when we're thinking about methyl, ethyl, propyl, etc. You go then from that to whichever direction, clockwise or counterclockwise, to do the lowest choice of numbers. In other words, we're still trying to get the lowest numbers possible, and we're going to start with the one that gets alphabetic priority. It does lead to some funny discussions at times, but let's look at a couple examples to see how that works. Okay, if we were doing this in class, we'd time it and take it for a couple minutes, and there's some cycloalkanes to look at. The ones each on this screen have a more detailed way to be evaluated. Pause the recording and make your own evaluations of what these should be named, and then we'll resume with describing their actual names. So here's the first one we'd like to do. The longest chain, or the parent compound name this time, is the ring structure. There are 6 carbons in that ring, and so we call that, think hard, cyclo, what? Just like other 6 carbon compounds, it's cyclo, but it's hexane. And then attached to that, we have a branch now, and the branch has, well, it's got to have 3 carbons, doesn't it? But let's use a different way of numbering these for a moment. There's going to be 3 carbons in the branch. Ooh, I hope that shows up okay for you. Not great. Could be better. And those 3 carbons in the branch tell us that this branch would then be a propyl type of branch. But it's ordinary propyl because they're not a branched substituent, but an ordinary one. And so propyl becomes the first name, propyl cyclohexane. Now, do I have to specify this as carbon number 1? No, because all of the carbons on the ring are the same. There's nothing different about the ones that are around it, so putting that number on there is unnecessary. Okay, that was a simple example. Let's do some more. Let's look at these structures here. We're going to do the one on the left first. These are the same ones from the previous slide. Let's see if we can determine what the proper name should be and use your powers of cleverness to see how these work. I'm going to give a different color. And the left structure has what for its last name? Is it going to be based on a ring? You bet. So let's figure out where the ring is. I see 1. Oh, I don't like that color after all. Let me fix that. Go back to red. Red was a good choice here. All right. So 1, 2, 3, 4, 5 in the ring. So cyclopentane is the right idea. Cyclopentylmethane? No, that's not a thing. So 3 isn't right. Is it going to be dimethyl? Well, let's look and see. If that's the ring, we could draw it like this. Whoops, sorry. And on one corner is 2 CH3 groups. That's what each of these are. And that's methyl groups. And so they're on the same carbon. Oh, that means that their number has to be the same. So it can't be 1 and 3 or 1 and 4. It's 1,1-dimethyl cyclopentane. All right, that's that one. Let's do another one. Part B of this diagram. What would the this is an isomer. Oh, we didn't finish talking about that. I'll come back to that. These are isomeric cycloalkanes, and we'll have to decide why in a moment. So the structure on the right has a cyclo of something. These all seem to have the same ending. Guess what? It must be cyclobutane. Do you see 4 in a ring? I think that makes sense. And then when you do 1, 2, 3, 4, we'll give the lowest number to the substituent, so it needs to be on carbon 1. Do we have to specify it? In this case, we don't, because there aren't any other pieces on the ring, so we don't need the number to complete the name. But now we have to explain this group over here. So there's how many carbons in that group? 3 carbons. But it's kind of what I would describe as a Y. If you redraw it like this, you've seen it like this in another diagram perhaps. It's not just regular propyl. This is the branched propyl, and so it's not propyl, and it's not the one, we didn't need that. Is it methyl ethyl, as in number 4? Nope. This is what we call isopropyl. Okay, these are some simple examples of cycloalkanes and how you name them. There's lots more to be learned from practicing on the homework. By the way, though, why are these things isomers? Good question to ask. Why are they isomers? Well, isomers have to have the same formula but different structures. Same molecular formula and different structures. Well, the formula for this compound on the left has 5 carbons in the ring and 2 more, so that's carbons of 7 carbons. And whenever it's an alkane, oh, but it's not going to be the same simple formula because we have a cyclic alkane. Now it's going to come up with a slightly different count of hydrogens. So counting on the ring, 2, 4, 6, 8, and then there's 3, that's 11, and 3 more is 14. So you end up with twice the number of hydrogens as carbons when it's a cycloalkane. On the structure on the right, we have 4 carbons, and we have 3 carbons, so for a total of 7, again, C7. And the hydrogens, surprise, surprise, are going to come out the same. But we have 2, 4, 6, and then we have 8 plus 3, which is 11, and 3 more is 14. So they are isomers. Same formula, different structures. I hope that helps you. Please ask lots of questions. Good luck on your homework. See you in class.